Hello there, this is Acer's OS and this is my application to the Open Redstone Engineers build server. Today I'm going to be making a 2-bit by 2-bit multiplying machine that will display the results of these 4 redstone lamps. So first, before I even start, let me go explain exactly what's going on here. So in binary multiplication, each bit can be represented as a 0 or a 1. Now, binary multiplication works the same way as decimal multiplication in that we take this bit times this bit, we find the product of that. So for this case, we're multiplying 3 by 2, so the 0 times 1 is going to be a 0. 0 times another 1 is going to be a 0 as well. Now, since we multiplied this second number by both these numbers, we effectively remove this and we shift a bit over to the left, and we do this by representing, we do this through a extra 0 we add on, and then we take the next number and we multiply it in the same order as the first number. So now we have 1 times 1, which equals 1. 1 times 1 again equals another 1, which will be right here. And then our solution is the sum of these. So the sum for this particular equation is going to be 0 here. We're going to have a 1 here and a 1 here. So we have 3 times 2 is equal to 6. And in binary, 1, 1, 0 is represented as a 6 in decimal. So we have the right process down. Now, this isn't the only thing that's going on in a machine that multiplies 2 binary numbers together. It's doing 2 things right here. Number one, it's multiplying 2 numbers together, and it's adding them. So first, let's tackle how do we multiply 2 numbers in binary together. So if we look at these 2 numbers right here, we have the numbers 0 and 1. That's our first product. 0 and 1 should equal 0. Likewise, if we multiply 1 by 0, we should get 0. Multiplying 0 by 0, we should get 0, and the only time we should get a 1 is if we multiply it 1 by 1. So the way we represent this logically is through a AND gate, where our inputs are right here. This is going to be input A, and this will be input B. So these would be your 2 numbers. So if both of these are on, so if we multiply 1 by 1, we should get a 1 for our result, which is true. If we multiply 1 by 0, we should get a 0. Likewise, if we do the other way, it should not matter. Or if we multiply 0 by 0, we get 0. So the basis of binary multiplication is a AND gate. So we take our 2 numbers, we throw them in the AND gate, and that's our result. That handles the binary multiplication part. Now after that, we do something called binary addition. So after we multiplied 0 and 1, we get a 0, and 0 by 1 we get a 0 as well. Say we had a different number and we had 2 1s. Or let's take a step back. Let's handle the addition part of this. So what we're going to need to do is build a thing called an XOR gate, which is an exclusive OR gate, which is true when one of the inputs is true, and that's our only case. So the way to build that is like this. I don't take credit for this design, but it's very handy for showing the answer, or showing how this process works, so I'm going to do it like that. So an important thing to know when doing addition in binary is if you have a carryover value. So in this particular case, if we're adding 3 plus 2, we take this first digit, our 1's digit in decimal, if you'd like to think about it that way, we add it together. So our 0 plus 1 is equal to 1. Now for this case, we have 1 plus 1, and in binary we can't represent 2 in a single decimal spot. So just like in decimal, when we have a carryover value, say if we added 5 plus 5, our answer is 10. But in decimal, the way to get a carryover value is if you add 1 and 1. Why do we do this? It's because the value 2 can't be represented in this single place value. So we have to zero out this place value and carry on to the next. And then we sum that column, which happens to be all 0, so we get a 1. So 3 plus 2 is equal to 5, which is this number right here in binary. So we have to mimic this in logic gates. We have to mimic this carryover to the next bit so we can add properly. And without it, we wouldn't be able to do binary addition. So what we have to do here is use an XOR gate and an AND gate combined, which is quite handy. So a basic XOR gate, what this is called is going to be a half adder. A half adder is a adder that adds 2 bits together but does not account for a carry-in value, while a full adder does account for a carry-in value. So in this example, we could have a half adder at this second bit right here, because there's no way in this particular problem that this first placeholder could carry a value over. So this does not have to have a full adder in it. So for example, say these are going to be our numbers. This will be our same number A, this will be number B. When the redstone is off, this is represented with a 0 in binary, and while it's on, this represents a 1. So if we add 0 plus 0, our output, which is right here, is going to be off. This is going to be our carryout value, which, if it's on, that means we can't represent the value from this equation in this bit, so we have to bring it to the next bit. So 1 plus 0, our output is 0, or his output is 1, I'm sorry. If we have 0 plus 0, likewise, we don't have any output because 0 plus 0 is 0 all the time. But if we have 1 plus 1, we can't represent 1 plus 1 through the first bit, through this bit, say. We have to carry it to the next place value. So how this is accomplished is we put an AND gate on top, and this is what the AND gate looks like. There's a torch right here that gets turned on when this is not powered and this is not powered, which means it's not inverting this torch, and this torch is able to light up the next placeholder value. This is how a adder works in binary. You just hook all of these up together. You have a bunch of these hooked up together, and you continue this carry, and you keep on having more digits. So this is the ones digit, or in binary it's actually called, it's still the ones digit. This digit right here is the second place value, 2 to the power of 1. This one would be 2 to the power of 2, and this would be 2 to the power of 3. This is exactly the same as decimal if this doesn't make too much sense. Pretend we're adding decimal numbers, so numbers 0 through 9. This would be 10 to the power of 1, or otherwise known as the ones. This is known as 10 to the power of 2, well, I'm sorry, 10 to the power of 0 right here. These are the ones. 10 to the power of 1, this is the tens digit. 10 to the power of 2, this is the hundreds digit, and so on and so forth. The reason why we use 2 instead of this 10 here is because we are in base 2. Decimal is base 10, and it's just how this binary addition works. Now, finally, we have talked a little bit about the mechanics behind multiplication. We know we have to use a AND gate to find the value, of two numbers being multiplied, and then we have to use those XOR gates, those adders, binary adders, to add the numbers up and carry digits over if possible, if needed. So let's get building with this. We're going to have two numbers. This will be number 1. This will be number 2. So let's label these number 2 and number 1. Now we have to represent each bit in a certain way, so what's easy for me is labeling bits by significance. So this bit's going to just be called A0. This is A1. This will be B1, and this will be B0. This on this side will be our output, our display of the equation. So we're going to display our answers just like we have in decimal, with the least significant digit, the 10 to the power of 0, or in this case the 2 to the power of 0, all the way to the right. And the next digit will be the next value, and I'll just fill these in right here. So if at any time any of these are lit, you take the equation up on the very top, and that is equal to your value. So let's get started with this binary multiplication. So the first bit we'll have to do is this least significant bit for both numbers. So that is A0 and B0. So we'll need to AND those values together. So we're going to take B0 and AND it with A0. So I'm going to make a little AND gate right here. This is not my design. I found this on the internet. And gates are okay to copy because there's a limited design on how they could be built efficiently, so it's okay to copy logic gates, but not circuits and stuff. So the value for this, I will represent the value of these as a light gray. So if we multiply, this solution is going to go into the least significant digit. 1, 2, 3, 4, 5, 6, 7, 8. Let's just put this here so we have a good signal. So if you pretend these two numbers are binary, we'll just cover this up. If we have two binary numbers, this is the first bit, this is the second bit. So if we have 0, 1, which equals 1, times 0, 1, we should get 1, which is correct. 2 to the 0 is equal to 1, and that's on. So that means we have an answer of 1. Now for other bits, we're going to need to multiply some things differently. So if you look at that diagram over there, multiply the least significant bit in one number by this digit, the most significant bit, and then we do it opposite. So we multiply this by this, then this by this. So we're going to need to multiply A1 by B0, so that's the two outer values. Let's do that. Okay. Just gonna lower this right here, make another AND gate. Oops. Flip this around. So in this calculation, let me just mark these so we know what's going on. This one we have A0 times B0, and in this one we have A1 times B0. Now what we're going to do is multiply B1 by A0, so we're going to multiply these two middle ones now. Put this repeater right here so it doesn't connect. So I want to mix up these AND gates, it'll mess up what we have. So now we're going to need to AND this. So we'll multiply this again. We'll make an AND gate right here to represent the multiplication that goes on. This is going to be, this has to be hooked up right here. I want to strengthen this signal. Then this one goes right into this. So the output for this particular bit is going to be right here. The output for this bit will be right here. Now we need to look at this and remember that both of these could be on at any point. And if both of them are on, we need to know to carry that one over there. So what we're going to do is make a XOR gate, which I'll use this color for. So if both of them are on, we'll have this torch up here letting us know that we have carry out, we have an output that needs to go to the next bit. But if only one of them is on, then this XOR gate will be true, and it will send output to the next bit, or it will send our output to our solution, or to our display, I'm sorry. So we need to hook up this one, so we'll let me get this wired up right here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's add one of these so we can have a strong enough strength. Okay. That's nice. Alright, so we've ANDed those two gates. Now we have one more AND gate to create, and that is the multiplication between that higher digit 1 and this digit 1, which are represented as A1 and B1. So we need to AND this far gate with this third one in. Let's put some redstone right here. Let's build it right here. I apologize if it's distracting, all that text going on. I know I had to stop the video a couple times, because my first instinct to do is to listen in and talk to people, but it's not the best idea to do that while you're making a video about this. Alright, so we have the bit right here. The final bit we need to multiply together. So we need to have this all hooked up to an XOR gate. And this will become our next digit that we display in the machine, in our display over here. And if you're wondering what this over here is, this is a 7-segment display. You can hook this up to one of those to show your numbers, your answers in decimal. I don't think I'll have enough time, and it doesn't really display a good knowledge of binary. I mean, encoding is a good thing to learn, but since this isn't about it's more about multiplication itself, I might do another video on how to hook it up. But besides that, I'm gonna add a repeater in here now. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Add one right here. That should be enough. Let's put one more just in case, because I like having strong signals in there. Cool. So that's the next bit. So in the process so far, we've taken the least significant bits, we have added them together in this output line right here to the least significant bit. Next, for these next digits, we're mimicking the same process in there. I took A1 times B0 right in this AND gate, so right here, this AND gate, I did that. And B1 and A0 in this one right here, this AND gate. And I put that into an XOR gate because both of these could be true. If both of them are true, I want the signal to flow into the next bit, which is the next bit. You can see it goes into this, overflow goes into this bit rather than this bit. But if either one of them, if only one of them is true, I want that solution to display in a bit before the overflow. And then finally, I took the most significant bits in both of these numbers. I used a AND gate right here, and that also goes into an XOR gate because we can't have overflow from this XOR gate. And if that's the case, we actually want to bring the signal to the last bit that we have, this bit, which is 2 to the third power, which is 8. I'm using a fancy redstone trick that I saw because it works very well. It's awesome. And we're going to bring this current all the way to that 8. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's put one right there. 1, 2, 3, 4, 5, 6, 7, 8. Alright, so now everything should be hooked up right. So if we take a number and we do 1 times 1, our output should be 1 like it was before. If we do 2 times 1, our output should be 2. If we take 3 times 1, the output should be 3. 2 times 2 should be 4, which is right here, 2 to the power of 2. 2 times 3 should be 6, which is 4 plus 2. And then the biggest bit we can get is 9, because we have 3 times 3, which is 8 plus 1. The reason why we can't get a 5, 7, or 8 as a solution, because 8 is 2 to the power of 3. Since we have two numbers here, we can't represent 3. We'd actually need 2 more bits. 7 is a prime number. We can't represent 7 unless we have a 3-bit number. 4 plus 1 is 2. Or 4 plus 2 is 6, plus 1 is 7. So we need a 3-bit number to represent 7, as well as 5. So we can't do this with a simple 2-bit multiplier. So I think I'm going to save the encoding and decoding for a separate video, but I hope this video was clear enough that people can further understand binary multiplication and how multiplication works with redstone in Minecraft. Thank you.